Hey everybody, it's Mrs. Harbin coming at you with video notes 10.2. So, just a little history lesson song going on in the background. I want you to think about this. Which picture do you think here is most likely? I'm thinking you think that is more likely than that. Not sure, but that's what I think. So, spontaneous. You might think of spontaneous as something you do at the spur of the moment, but spontaneous in chemistry is a reaction that is spontaneous if a reaction is spontaneous if it proceeds on its own without outside intervention. Okay. It occurs naturally. So rock rolling down the hill is spontaneous. Rock rolling up a hill is not spontaneous. Have you ever seen a rock roll up a hill on its own? No. But have you ever seen a rock roll down a hill? Once it gets started, it's rolling. Okay, so spontaneous is a process that occurs on its own without outside intervention. Okay, so here's some examples. Rusting of iron. So, it's mater, and it's mater. Rusting of iron is iron plus oxygen turning into iron oxide. All right, and so of course we have 2 of those and 3 of those and 4 of those. It's a spontaneous reaction. It's a spontaneous reaction that occurs in that direction. Okay. There is a block of ice and it turns into a puddle. Now this is spontaneous in that direction at certain temperatures. Okay. So it happens without outside intervention. This top one happens at any temperature without outside intervention, so it's spontaneous. This bottom one is spontaneous at some temperatures. Okay. So spontaneous means happening without outside intervention, and it has nothing to do with rate, though. So let's look at this. Spontaneous does not mean rapid. It doesn't mean it happens fast. It just means it happens. It might take a long, long time. So you could have a rapid spontaneous reaction, but it doesn't have to be. Or you could have a slow spontaneous reaction. You could have an explosive spontaneous reaction, but it doesn't have to be. Or you can have a non-explosive spontaneous reaction. Okay. So I just want you to be careful. Remember, spontaneous does not mean rapid or explosive, although it could. Spontaneity doesn't tell about rate. That's what all the mechanism and reaction rate and collision theory was for. Okay, so outside intervention. I said it happens on its own without outside intervention. Some spontaneous reactions require an initial spark, but they're still considered spontaneous. What is that initial spark for? Well, every reaction goes up first, then down. Goes up first, then down. So the initial spark might be the activation energy it takes. But for a spontaneous reaction, once it's gotten that activation energy, it continues. Okay, so non-spontaneous reactions can also occur, but in nature mostly spontaneous reactions occur naturally. Non-spontaneous reactions occur only if a lot of energy is supplied. Okay, so here's the 2 skiers. Whoa, they're having fun, right? One of these is skiing in the spontaneous or natural direction. The other is skiing in a non-spontaneous direction. Hopefully you chose spontaneous, not spontaneous, and this could happen as long as there's a lot of extra work to make it happen. Okay. So maybe you get now what spontaneous means. It means goes in a direction that is happens without outside intervention. So how do we quantify that? Well, we have this value called Gibbs free energy. Gibbs free energy, delta G. What is Gibbs free energy? Well, it's the energy given off to the surroundings or absorbed by the surroundings after all the bond breaking and forming and energy dispersal has taken place. Okay, so remember, bonds break, bonds get formed, things rearrange, and if there's extra energy left over, that's called Gibbs free energy given off. If there's extra energy that has to be added in after all that bond breaking and making to make it happen, that's Gibbs free energy being absorbed. Okay, so Gibbs free energy is the energy available to do work. If it's given off, then it can do work on something else. If it's added in, you have to add in extra work to make a reaction happen. Okay, so a negative delta G is Gibbs free energy being released from a chemical reaction. What can that mean? Well, if you cook a steak, that's not the chemical reaction we're looking at right now. We're looking at the burning charcoal. Okay, burning charcoal. You have your charcoal in the grill, you light it, you maybe use lighter fluid, and you get it going. But once it's going, the atoms are rearranging, bonds breaking, bonds forming. It's exothermic, and then all of that happens, and after that there's extra energy given off to cook your steak. Oh, there's Chewy. So that's one example. The burning of charcoal, it releases Gibbs free energy that can be used to cook a steak. If you want to run a steam engine and you have a spontaneous combustion reaction going on in the steam engine, that's charcoal again, but it's used to, the extra energy given off is used to run the steam engine. Okay, so Gibbs free energy release is a negative G, and that's a spontaneous reaction. Any reaction that gives off Gibbs free energy means it's spontaneous, and it means there's extra energy released to do work in another system. Okay, so what's the opposite of that? Positive delta G means not spontaneous. Not spontaneous. Positive G is not spontaneous. So that means that extra free energy has to be absorbed even to make all of the rearranging and breaking bonds and making bonds happen. Okay, so this going that way is a negative delta G. All right, but this going that way is a positive delta G. You have to add a lot of energy in to really reverse the iron oxide that forms here and turn it back into shiny nails. But extra energy is released, Gibbs free energy is released when the nails turn into rusty nails. Okay. Also, if you want to recharge a battery, you have to do a lot of work to make that chemical reaction be reversed. So you have to add in extra free energy. Okay. So there are three possible ways to represent delta G. You can have a negative value, and anytime you have a negative delta G, that means free energy is free, given off to do some other work. So that's spontaneous. You can have a positive delta G. If delta G is absorbed, then it's a non-spontaneous reaction because extra free energy has to be added in to make that reaction go. So that's not spontaneous. You can also have delta G equals 0, which means both the forward and reverse chemical reaction can occur at the same rate. And that's what the next chapter is about. Woohoo! So, how, if you don't know delta G is positive, negative, or 0, what two factors can help us figure out delta G? So delta G is spontaneity, Gibbs free energy. If it's negative, it's spontaneous. If it's positive, it's not. Delta G is 0 is equilibrium. What if we don't know that value? Where there are, well, there are other factors that can help us. Okay, so two factors help us determine spontaneity. They are enthalpy and entropy. We've talked a lot about enthalpy because that's heat, and I introduced entropy a little bit in the last video notes. So talk about heat one more time. Hey, look, delta H enthalpy heat. Hey, you want to see that again? Delta H enthalpy heat. All right, one more time because it's cool. Delta H enthalpy heat. Keep that in mind. It's one of the driving forces for any reaction, especially spontaneous ones. Enthalpy is the heat content of a chemical reaction. So the favored conditions, the ones that are going to help us get a spontaneous reaction, is a negative value for delta H. So that means exothermic is a naturally favored state. Here's why. Here's the energy diagram. All right, these are reactants, these are products. This is lower energy. Lower energy is a favored direction for reactions. So lower energy, favored by nature. Lower energy, favored by nature. Okay, so delta H negative is favored by nature. Okay, so many exothermic reactions are spontaneous because they result in lower energy content of the products. Some reactions are endothermic, are spontaneous. You saw that ice melting was spontaneous at a certain temperature. How can that happen? Well, there's another factor that's called entropy that also drives the force, drives the reaction. So look, entropy is dropping out, and there it is. Okay, so entropy is sometimes defined as a measure of the disorder or randomness of a substance, and its symbol in is S. Hey, wait a second, that's totally random. That's good because it's disorder. Okay, so delta S is entropy. The favored condition for entropy, which also helps decide if a reaction is going to be spontaneous or not, is one that increases in entropy, one that gets more entropy, gains entropy. In other words, entropy is a naturally increasing entropy. More entropy, good. Okay, increasing delta S is favored by nature. So here's some examples. Increasing disorder. Okay, so look at this. There's a structure in solid. Okay, in a liquid, the molecules are able to move around more. there's more combinations of different types of energy at this higher temperature, and so those molecules have more entropy. In a gas, they can go wherever they want. So there's more combinations of possible energy for a gas based on its position and its motion. Okay, so that has the most entropy. So, which state of matter do you think has the greatest entropy? I may have just told you, but if you said gas, you're right. State of matter with the lowest entropy, if you said solid, boom, you're correct. Yes, we know. So, just to help you remember, delta S is entropy, and entropy is disorder or dispersal of energy over a variety of molecules. So how can you look at a chemical reaction or describe when entropy is increasing? So make sure you have these four things understood. Okay. If a gas forms in a chemical reaction that started out with liquid or solid products, then more entropy is occurring. Okay. It's an increase in entropy. If you start with a liquid or solid and you make a solution, so reactants are liquid or solid and products are aqueous, then there's increased entropy in that reaction. If there's more gas particles in the products than there were in the reactants, that's increased entropy in that reaction. And increased entropy, so positive delta S for all of these. Okay. If the temperature of a substance increases, then it also is increased entropy. So here's a visual of that. You could see which one has a wider dispersal of energy. This one. So that's increased entropy. More entropy. More entropy. More entropy. So if it turns darker red, this is just indicating a temperature change. If the temperature of this system is greater than the temperature of that system, then there's more distribution of energy if you look at all of the particles. Okay. So there's a thermodynamic law that helps us understand entropy. It's the second law of thermodynamics. And entropy of the universe is increasing. What's with that E? Okay. Where are they going? Oh, it's increasing in entropy. So now that you know about this law of thermodynamics, you can explain why you have a messy bedroom. You know, say, Mom, I can't clean my room. It's against nature's way. Or, Mrs. Harbin, look at this exploding binder or this exploding folder. AKA, Colin, I saw your folder. It's the law of thermodynamics. Entropy is prevailing. Okay, so spontaneity. So we started with what makes a reaction spontaneous, and now we're going to look at how these work. So enthalpy. What's nature's favored push of enthalpy? Heat. Lowered heat. So negative enthalpy is one way that heat can go. Now if we combine that with entropy, what does nature prefer with entropy? Nature wants increased entropy. So if both of these factors are going in that direction, then do you think you're going to have a spontaneous reaction? Well, that's favored by nature, so the answer is yes. Okay. So this is favored way. Okay, it's the natural way. Okay. Some reactions are exothermic. That's negative. I said exo, I meant endo, my bad. Positive endo. Okay, endothermic. Some reactions decrease in entropy. So if this were the case, this would not be favored. Okay, so it's like, oh, nature doesn't want endothermic. Nature doesn't want decreased entropy. So that reaction will never be spontaneous ever, ever, ever in that direction. Okay, favored, favored. This is exo. This is more entropy. Okay, that's favored by nature. That's spontaneous. Not favored. So endo and less entropy are not favored. So that's going to be not spontaneous ever, ever, ever. And then if delta H is negative, that's exo. That's favored. Yeah, we'll take it. Oh no, this is less entropy. Negative entropy, negative S is less entropy. That's sad. So what happens here? Maybe your reaction can be spontaneous. Okay, well, same with the other one. This is endo. Not so happy with the naturally occurring. Okay, this is more entropy, so that's favored. All right, so it's favored. And so that's also a maybe. All right, so what does this mean about delta G? Well, we just found out that enthalpy decreasing, entropy increasing means spontaneous, and we already learned that spontaneous delta G is negative. Okay, this is against nature, not spontaneous. So we have positive delta G, which means not spontaneous. But then these maybes, we need a little more information. And we already know the delta G equation. That little more information would be the magnitude of the H, the magnitude of the S, and the temperature. Okay, so if delta H and delta S are both positive or both negative, the reaction may or may not be spontaneous. So we can use this quantitative way to decide. Okay, so what's the G? Gibbs free energy in kilojoules per mole. The H is enthalpy, kilojoules per mole. The temperature has to be in Kelvin. Okay, so degrees Celsius changes to Kelvin by adding 273. 273. Okay, Celsius to Kelvin by adding 273. And then S is entropy. Notice the units on entropy, joule per mole Kelvin, and notice the units on temperature. If you multiply those together, what cancels? The Kelvin cancels, and then you get joule per mole. All right. Just be careful because some data tables give you entropy in kilojoules, and so you just have to change it to joules if you want to plug in any of the other factors. Okay, so let's use this to make sure we can understand what spontaneous reaction is. All right, so if this is negative, going nature's way, you subtract off T. Temperature is always positive because we started 0 Kelvin, so it's always positive. So if delta S is positive, negative minus positive plus negative, no matter what, if entropy is increasing and enthalpy is decreasing, delta G is going to be negative, so that's spontaneous. Woohoo! Okay, so this is exo, this is more entropy, and then we get spontaneous. All right, what if delta H is positive? So that's endo, not the naturally preferred way. Temperature is always positive, so minus. If the delta S is negative, that is less entropy, also not a favorable situation, so plus a positive. Delta G will always be positive, and so with those two conditions, your reaction will not be spontaneous. Okay, so you might be wondering, well, how can I calculate the delta S? It's very similar to the delta H. So we're going to say of the reaction is going to be the sum of the delta S of the products, make sure you do products, minus the sum of the delta S of the reactants. Okay, very similar to what we've done already, but now we're talking about a different factor, the disorder of the system. So let's see, we got products, HNO2, and that's 46.1 joule per mole Kelvin, times the coefficient of 1, which cancels that out, 1 mole, plus the 53.5 joule per mole Kelvin. So what I'm doing is I'm calculating the delta S for the products right now. And so far I get 99.6 joule per Kelvin. Okay, so it's the products, delta S of the products, minus, I need delta S of the reactants. Okay, to get the delta S of the reactants, here's H2O 69.9 joule per mole Kelvin. And 2 times 211 joule per mole Kelvin. All right, up 2 times moles. All right, so we get 422 plus 69.9, and that gives us 400. Wow, 91.9. All right, so plus and negative joule kelvins tells us that delta S for this reaction is negative 392.25 joule. Sorry, I put joule. I put kilojoule. Joule Kelvin. Okay. So why isn't delta S ever 0? Because the only time something doesn't have internal energy is at 0 Kelvin. All right. And so delta S will always be the energy in a substance. Does state matter? You betcha, because we know that S of a solid goes S of a liquid, S of a gas increases. Higher, higher. So state does matter, yes. Okay, so that's how you calculate delta S. Similar. Okay, equilibrium is when delta G equals 0. Some reactions happen in both directions. So this reaction can happen forward and reverse. This one's tough to do. if you make a precipitate, all right, so pour stuff in, and then you get solid, that's actually reversible as well. Combustion is not reversible because when you burn something, burning. You make carbon dioxide gas, water vapor, ash, all right? Trying to get all of those things back together to make the original material that burned is not possible. Okay, this is spontaneous in one direction only. Okay, so here's what I want you to remember, this formula. Delta G equals delta H minus T delta S. So don't forget that boxing hippo says calculating delta G to find out if it's spontaneous or not. You might have to calculate H, calculate S, plug them into this, and figure it all out. Don't forget to make sure your temperature is in Kelvin. Thanks, boxing hippo. And now I want you to realize that nature's way is towards more disorder in the universe, right? So when the walls come tumbling down, that's for sure increasing entropy, right? So let's take you out with that. Thanks for playing. All done.